It's accurate.
Okay, so now this is not in the molecular geometry / Vesper chapter. This is in another chapter, but this goes along with compounds and shapes and everything like that. Goes along with whether something is polar or not. Okay.
Can you see that? I don't know.
Oh, can you even see that, Jacob?
Yeah, I can see it.
Okay, okay. All right, so what we're going to be talking about is intermolecular forces. What intermolecular forces are attraction forces between molecules, compounds.
Sorry, I spit my gum out.
Okay, now one thing to kind of note, intermolecular forces are weaker than intramolecular forces. Okay, so what are intramolecular forces?
Not between.
Close.
Would it be like the same molecule? Yeah, they're within a molecule compound.
Alright, so intramolecular forces, not inter, but intramolecular forces are bonds. So covalent bonds, ionic bonds, metallic bonds. Okay? Now there's three, I guess you can kind of call them the main three, but there's technically four that we can kind of look at and talk about. Two of them are going to be real close to one another, and we'll discuss that, but that's what we're going to be doing today, looking at that. Then we're going to learn how to identify what kind of intermolecular forces a compound can possibly have. Okay? All right, so let's start with our, these are considered to be the weaker of the intermolecular forces. Okay? These are the van der Waals forces. Van der Waals. Where do you think he's from?
France.
Go a little bit east.
Asia.
You went way too east. Go back west. Europe, yes.
Germany.
Closer. Probably Austrian, Switzerland area. Okay.
Close.
What's east from
Yeah.
France?
You were close for it.
I'm not
But he's like east. I was like.
Okay, so our first one.
London.
Under the van der Waals forces, first one is called London dispersion. Now, London dispersion force is an instant dipole. Now, looking at the word dipole, what does that prefix di mean? Two. What do you think pole means? Not Miss Mary sitting on a fence.
Two poles.
Two poles. Yes, but what kind of poles are we talking about here?
Opposite.
Positive, negative, right? Opposites. Okay, so dipole. We're talking about a positive, negative polarity one at one end of the molecule, the other at the other end. So when we have a polar molecule, yes, we have one end as a positive end, one as a negative end. Now this instantaneous dipole that we get, this is due to I really hate this thing bouncing back and forth. It's due to the movement of electrons. Now to kind of show you how this works out. Good to go, Jacob?
Yeah.
All right. Let's look at a helium atom. Helium atom has how many electrons to it?
Two.
2. How can we know that has 2 electrons to it?
This way.
Learned that.
What number is helium? 2. Okay? So, let's look at the planetary model of helium. So it has 2 electrons, that means it has 2 protons, right? Now, since they are spinning around, usually they're at opposite ends of one another. Okay? And the electrons are spinning around really, really, really quick. And what eventually could possibly happen is that, since they are spinning around so much, they catch up to one another. So since the 2 electrons are at one end of the atom, we can kind of say that the protons are at the other end. This is where we get that instantaneous dipole. Because we got a partial positive on one end and a partial negative on the other end. And as quickly as it is formed, it quickly disappears. Okay? In an instant. All right, some things about, yes.
So, would the same thing be constantly acting with hydrogen because it's only got the 1 electron?
Well, since we really won't have one hydrogen atom floating around by itself, no.
Oh, alright.
Okay, since, because hydrogen is one of our diatomic molecules,
Yeah.
that's the reason why. Good question, but we won't see with hydrogen. Okay? Now, something with London dispersion. All compounds are going to have London dispersion forces. All right?
Make some more noise, please.
No questions? Okay, so that's our first intermolecular force. Now the second van der Waals force dipole-dipole interaction, or dipole-dipole interaction. You gotta make this fun somehow, because this is one of the topics in chemistry that a lot of chemistry teachers hate dealing with. I think it's kind of easy. All right, so dipole-dipole interaction. Attraction between polar molecules. Now, something that we need to kind of note about with these two, so put a star by this bit of information. molecules of approximately equal mass and size, the strength of intermolecular attractions increase with increasing polarity. Okay, so what in the world does that mean? Anybody? We have compounds that are roughly same size, same mass. Why does the intermolecular forces increase with increased polarity? Anybody? Owen?
Well, with increased polarity, that's like the more polar a molecule or atom is. And so because it's an attraction between polar molecules, then it only makes sense that it gets stronger the more polar the molecules are.
Okay. So we said, kind of go along with it. London dispersion happens in all compounds, right? If we're working with a non-polar molecule, are we going to have a dipole interaction with it, with any other molecules? No. Okay. So the only kind of intermolecular force that a non-polar molecule is going to have is London dispersion. Everybody with me? Now, if we have a polar molecule, we have London dispersion, and we're also going to have dipole-dipole interactions. So we're going to have more intermolecular forces or intermolecular attractions with polar molecules because we have more forces happening with it. Okay? Does that kind of make some sense now? Yes, no? Rattle your heads? It's Tuesday, I know. Should I have snow day?
Feels like a Monday.
Feels like a Monday? Well, if you were here on Monday, then today would be
Feel like
Tuesday.
Monday.
Okay, now, actually, yeah. Along with dipole-dipole interaction, we can have ion-dipole interaction. So with an ion-dipole interaction, we have an ion and a polar molecule interacting. Why would that happen? Why would we have an ion and a dipole interact with one another?
Either one.
Because they're opposite charges.
We have, well, let's take out one word from that sentence. We have charges. Okay? So ion has a charge, right? Dipole has partial positive and partial negative charge on it somewhere. Since they both have charges, they are going to interact. There's going to be attraction. This is the reason why we can make salt water. This is the reason why you put chlorine in your pool and it keeps it clean. Okay? Because if we didn't have this, then you really wouldn't have a pool. You just have a really nasty big tub of water, which some people might like.
And what do you call the ocean?
Well, the ocean actually is a big pool because it has, if we didn't have this, then the ocean wouldn't be salty.
Wait, why does chlorine kill everything else besides us?
Oh, you know it's not coming.
Yeah, Lauren. I mean,
I'm gonna say it's probably because it's not concentrated enough to be lethal to.
It's,
Okay,
to
okay.
use
You're
us.
not supposed to
actually,
put it in
he's
pool.
on the right track. If you, I mean, if you put a huge amount of chlorine into a pool, yeah, you probably kill a horse,
oh, cool.
okay? But
How do we go swimming?
because if you test the water of a pool, a lot of times the chlorine count is gonna be in parts per million, minuscule amount, okay?
It's parts per thousand.
Then that can be where things, because the smaller you are, that concentration can become lethal,
Oh, well, I'm dead.
okay? Because you kind of think, all right, tiny little microbe floating around the pool. Here comes chlorine. What do you think that chlorine's going to do to that tiny little microbe?
Eat it.
Kill it. Okay? Sometimes you gotta, since we are a bigger organism than a tiny little microbe, our bodies can adapt to that. And it's not that strong enough concentration.
But does it like still affect us, like in a small way?
It possibly could. You know, not everybody has, you know, everybody's physiology is just a little bit different. Because some people are allergic to certain things, like some people are allergic to chlorine. So if they go swimming in a pool that's been highly chlorinated, their skin's gonna come out very, almost like a rash. That's why some places, instead of using chlorine, they use bromine. Because it's not as harsh on your skin as chlorine is.
Would that change the color of the water?
No, no. Because
Diluted enough.
at the Y, when I worked there, at least I knew when I went there, they would use bromine to clean the pool. It's supposed to cost less, but the big problem with bromine is that it attacks stainless steel. So you gotta scrub and scrub and scrub and make sure that rust doesn't start forming on stainless steel in your pool. And it really isn't, I mean, if you go swimming in a brominated pool, you don't have that, you know, your eyes are all bloodshot. If you went into a chlorine pool with bromine, that's not gonna take place. So,
How do you know the difference between chlorine and bromine, like in the taste?
actually.
Well, I don't eat the water.
I really don't try to drink pool water.
Listen,
Yeah.
I think it could possibly
if I get the
kill
pool and my
you.
mouth happens to be open, like, who knows?
That's why I keep my mouth shut.
I'm not good at that.
Why do you
Yeah, but
swallow
some, like,
it?
my brothers like to kind
It
of
happens,
drown me.
but I-
and-
Well,
No,
what
but
is
it
he
doesn't
gonna do?
happen.
Spit it out and get it
Yeah.
on everybody else?
And then every-
But-
Yeah, not in my body. I'm spitting it out.
Honestly, all right.
You were never allowed to
Bromine,
spit it out.
brominated pool water and chlorinated pool water.
If I'm thirsty and I'm in a pool, there's water.
There's not that much to it. It's more of a smell. If
Relationship.
anybody was listening,
I heard that.
I heard you. No.
Because I'm interested.
but that's
in
the reason why.
As long as you drink it as it comes out of like
Need
the
to go back
filter
home.
part, you're good.
Yeah.
No.
Okay, so let's kind of look at some examples real quickly before we go on to our next intermolecular force.
We just go home. Like, Kirkman's the only person I'm gonna miss.
All right, so look at a couple different molecules that are roughly the same shape, same size, same mass. Propane, formula C3H8.
Oh,
Okay, next one, dimethyl ether. Now, these are the same examples that I had on the video that's on YouTube already. So I know at least one person watched it. I don't know who, but someone did.
Dang.
Where are these bamboo?
probably.
I don't know. I
Problem.
think they are. Do you have an eraser up in the house?
I mean, on my Chromebook, my account,
Oh,
I subscribe to him.
Thanks, sir.
I do the notification.
I'll get around myself.
There you go.
It's fine, it's fine.
acetaldehyde.
Sometimes I think they just throw some letters together, I mean, honestly.
This is my domain, organic chemistry.
I heard everybody fails that class in college.
No, not everyone.
Yeah, there's people. You didn't fail.
I didn't fail, I got a C,
Hey.
but I worked my butt off to get that C because, there's a lot, I mean, I'm not the smartest person in the whole wide world, I know that for sure. There's a lot of people that would beat me in the lecture, but they could not touch me in the lab. And this is one of the few times I'm gonna put myself on a pedestal, yeah, I'm that good in lab.
C's get degrees, is what you said.
Yeah. Well, my brothers say D's get degrees. So.
Mine
It's a different
different.
issue.
And the last one is acetonitrile.
I mean, I'll either way. You got a D plus.
Okay, so real quickly, try to draw the Lewis structures for these. Now, I gave you the formulas, try to figure it out.
I didn't leave enough room for that.
Whose fault is that?
I think you have more paper in that notebook there, Beth.
Well, I wanna like write everything in words, so then I know what to compare those with. You know what, Adam, shut up.
School just really has a
Did you do
concept
this
of
to
like-
English?
I do what now?
So you did.
Oh, like write down stuff from the.
Yeah.
What notes?
For the movie?
Yeah.
Lauren, we've already talked
supposed
about
to have
this.
notes, because I just wrote down each
Remember, that was
character
before 8:15, so they probably weren't here for
That is true.
and then
Oh, wait, I
wrote
didn't-
nothing.
3 times 4.
Okay.
What is that?
I don't know what you said, Stephanie.
I know you completely checked out when I was talking.
Should be determined.
Can you blame it?
Adam,
Yeah,
I
I can't
swear,
blame you.
stop.
You swear, Stephanie?
Yes.
That was intense.
Yeah, she's gonna beat me up.
Oh my
I will
gosh.
beat you up, actually.
I'll be shaking in my shoes. Just Lewis structure?
Just the Lewis structure.
Okay.
Now, I'm gonna give you some more information about these, just one more piece of information. We'll talk about that. Excuse me.
Whoa.
Yeah.
What are you okay with it? What do you even bother asking? I know the answers.
Bless you.
Hey, now. Quick.
just kind of help us along, but you kind of see by the little structure as they are. Anybody kind of coming up close to the same thing I had up here? Okay. Now, as I said, all four of these molecules, their masses are real close to one another. Might not be the exact same, but within 2 to 3 grams of one another, okay? All right, so now what we're gonna do is we're gonna look at the boiling points for each of these. So propane's boiling point, 231 Kelvin. Dimethyl ether, 248 Kelvin. Acetaldehyde, 294 Kelvin. And acetonitrile, 355. All right, so now, what kind of intermolecular forces are we going to see with these? First one, propane. We just have carbon and hydrogen. So is this going to be a polar or non-polar molecule? What do you think? Polar or non-polar?
I would say.
The difference comes out to be what we found out on Friday was right around 0.37.
Non-polar.
So it's going to be non-polar. So something you might want to write down in your notes or put in as a mental note in your head. Carbon and hydrogen bonds, that's going to be non-polar. So if we have an organic molecule that is just carbon and hydrogens, it's a non-polar molecule. Okay? So since this is a non-polar molecule, what kind of intermolecular forces are we going to see with this? London dispersion. Remember, because every molecule has this. Non-polar molecules, this is the only intermolecular force that we're going to possibly have. Okay? Dimethyl ether, acetaldehyde, acetonitrile. Polar or non-polar? You want to go to trial with that?
No.
Okay.
Really don't.
How can we tell just by looking at it without going through, figuring out the difference in electronegativities? We'll look at what we have in the formula. 2 of them we have oxygen. Third one we have nitrogen. Okay? Fluorine, oxygen, nitrogen. Those 3 elements are the most highly electronegative atoms. And when they are bonded to, let's say, carbon or hydrogen, they're definitely going to have a polar bond to them. Now, this one, oxygen, has 2 lone pairs in it, right? We kind of learned that lone pairs make that molecule asymmetrical, correct? Guess what? That's going to be a polar molecule. acetaldehyde. Oxygen with lone pairs. Polar and nonpolar. Polar. What do you think about this one? Even though it's not oxygen, we have nitrogen. This one's going to be polar as well. So are the other remaining three are all polar molecules. So what type of intermolecular forces we're going to have? Well, for one thing, we're definitely going to have London dispersion. The other thing that we're going to have with them is dipole-dipole. Okay? So we can kind of see 248, 294. That's a lot higher than 231, right? So when we have an increase in intermolecular forces, our boiling points go up as well. Now look at acetonitrile. This boiling point is 355. Higher than propane, which is down at 231. Reason for that is, since we have a lot of intermolecular forces, the molecules are trying to be attracted to one another. They do not want to escape. Okay? Now, why do you think acetonitrile is so much higher than acetaldehyde or dimethyl ether?
If I had to guess, I'd say it's because the nitrogen has a triple bond.
Well, not just the nitrogen, but it has a triple bond in it. The last three do have highly electronegative atoms. Agree? Now let's look at the types of bonds we have. In dimethyl ether, from the oxygen to the carbons, we have a single bond. In acetaldehyde, we have a double bond. Acetonitrile, we have a triple bond. As multiple bonds increase, their distance between the atoms decrease. Okay? So a triple bond is the shortest type of bond that we could possibly have. It's very rigid. It doesn't like to move a whole lot. Double bond is right in the middle. It can move a little bit. Single bonds, they're the longest ones. They can move around a whole lot. Okay, so to kind of show you, here is a double bond. Waggy. Single bond. Moves all about. Triple bond, it doesn't like to move, barely at all. So, since it has a shorter distance than double bond or single bond, it's going to have a lot of energy, and what we're going to have is we're going to have a greater dipole moment with a triple bond than what we are with a double bond or a single bond. Single bond, the dipole moment is going to be a lot less. Now on Thursday, I'll show you the calculations. I'll show it to you. I really don't think you'll really need to know it for the AP test. Okay? But since this has a greater dipole moment, that's why its boiling point is so much higher. It's more polar than the acetaldehyde or the dimethyl ether. Okay? Questions? Any kind of questions there? Nobody? All right. So let's go on to our third molecular force. Hydrogen bonding. Okay, so with hydrogen bonding, what's one of the things we're definitely gonna be looking at, Cindy?
Water.
It does have hydrogen bonding, yes.
Hydrogen.
We're gonna be looking at hydrogen. Okay? So hydrogen bonding,
Hey, I still got it right, so.
this is where we have an attraction between a hydrogen atom that is attached to a highly electronegative atom. Now, which three did I say were the most electronegative?
Nitrogen, oxygen,
Nitrogen, oxygen, and fluorine.
yeah.
Okay. In a nearby small electronegative atom on another molecule. Okay, so what Lauren said, water has hydrogen bonding to it. It's a very good example of hydrogen bonding. So what does that look like? Well, okay, so we have our water molecule, right? Oxygen, two hydrogens, and on the oxygen we have two lone pairs, right? So to make this, to show the polarity of water, since the oxygen has the two lone pairs on it, it would be the more negative side of the molecule, and the hydrogens would be the more positive side. Now this little doohickey that I put with it, that's called, I think that's sigma, and that's supposed to represent a partial. So oxygen has a partial negative charge, the hydrogens have a partial positive charge. We can see that the hydrogen is attached to a highly electronegative atom. It's attached to oxygen. Well, let's put another water molecule right here. So what happens in hydrogen bonding is that the hydrogen from one atom is attracted to a electronegative atom in another molecule. So this hydrogen is attracted to that oxygen. And if we put another one in here, this hydrogen will be attracted to this oxygen, then there, there. And as the more water molecules that we show, the more attraction and the more hydrogen bonding we can see between the molecules. Hydrogen bonding gives water properties that we see in it that we don't really see in some other liquids. For example, if I put some water, actually, let me go get some real quickly. Okay, so in my hand I have pure water. How do I know it's pure water? It's been deionized. So no ions whatsoever. Okay, Now, but look at what, did it just run everywhere? No. And if we look down, I mean, if we got down eye level with it, what do we notice what's happening to the water? What does it do? It domes. Other liquids, like if I had, if we had propane as a liquid and put it out on the countertop, since it only has London dispersion, that's it, it's a nonpolar molecule, it would lay flat. But since water has hydrogen bonding to it, water molecules are trying to attach to one another or be attracted to one another, so they're kind of binding up, and that causes water to dome. Okay?
Is that what causes surface tension?
Yeah, that's the biggest thing, that why water has surface tension is because of the hydrogen bonding. Some other, if we were looking at just a polar molecule, and then one that can't have hydrogen bonding, would it have some surface tension? Yeah, but not as great as one, a molecule that did have hydrogen bonding in it. Okay? Questions? Any kind of questions? Nope? Alright, so let's kind of get some information about these and how we can compare intermolecular forces from one to another. Alright, so point number one. Okay, when molecules of two substances have comparable masses and shapes, the dispersion forces are approximately equal in the two substances. Okay, point two. When the molecules of two substances differ widely in masses, and we have no hydrogen bonding going on, dispersion forces tend to determine which has the stronger intermolecular attractions. So which one do you think is gonna, if we're looking at two that have difference in masses, do you think the larger mass or the smaller masses are gonna have the larger attraction forces? Stephanie?
The smaller one.
Why?
I really don't know. It's a 50-50 shot.
True,
Just pick one and
true.
go for it.
What?
Just pick one and go for it.
Okay, so why'd you pick the small one?
Because I feel like it's a trick question. You want to say larger, but it's wrong. So I said smaller.
You might wanna go along with what Stephanie said?
Not really, she's always wrong.
Lauren.
Okay, but this one,
Water. Sorry.
it wasn't a trick question.
Dang it. Once and lose. Frank, you didn't know that. Shut up.
So you was awful.
The molecule that has larger mass is gonna have the greater intermolecular attractions. Why? You wanna try to venture a guess?
We see how my guessing goes. It's never.
But at least you learned something.
You're right. Yeah. I'm lost. No.
You might wanna help out. Adam?
Is it like gravity? Like, there's more, it pulls more, it's got more mass to pull.
Since it's got a bigger mass, it's gonna have a lot more ability for attraction to happen. Kind of think, you got more atoms to do that with.
Oh, that makes sense.
See?
Okay.
Alright?
Bert, don't even pretend you knew that.
Maybe she did
I'm
that.
just the face of this class. Okay.
She said she was the face of this class's stupidity. It's okay, Stephanie. That happens. Do you guys know you have like the same phone case almost?
It's the
Yeah,
exact
we
same
think
one,
so.
except
I thought it
mine's
was.
clean and hers is
Yeah,
dirty.
that's why it threw me off for a minute.
Oh, well.
Yours is like the same color on the one part. It's okay, Stephanie. Maybe next time.
Even your phone case is slowly falling apart.
Don't hate on it.
Don't hate on mine.
Okay. You got two compounds up on the board. Try to figure out what kind of intermolecular forces each one's going to have. Then try to figure out which one's going to have the greater amount, the greater attraction of intermoleculars. See if you can figure that one out. What type, which one's going to have the greater amount?
That's awkward.
Are we doing all right on battery life with the camcorder?
I don't know.
It hasn't come up with low battery, has it?
No,
Okay,
I
so we're
don't
good.
think so.
We're good. Now, as you're working on this Thursday, we're gonna be doing a lab. And it's gonna be inquiry-based learning. You gotta figure out why.
Oh, I'm not good at that.
And it deals with molecules, and it deals with intermolecular forces. It's a really easy lab to do as well.
She's here.
I'm good. I'm good too. That's Stephanie. We're probably friends.
Are we done? No?
Well, I didn't know how to do it, so.
It's just Steven.
Well, first figure out what kind of forces, what kind of intermolecular forces we're gonna have in each one. With that, we gotta look at at least look at the Lewis structures. Then two, this is probably the more harder one, we gotta figure out which one's gonna have greater amount of the intermolecular forces. And that's where I'll help you out.